We are going to start the chapter P block elements. It is part 1. So group 13 elements. Ionization energy. The first ionization energy of group 13 elements or boron family are lower than the corresponding elements of group 2. This is due to the electronic configuration of group 13 elements Ns2 and P1, and the electron thus has to be removed from the p orbital, which is much easier than removing an s electron of elements, which is more strongly attracted by the nucleus. Boron has higher ionization energy than its group members because it is considerably smaller. The ionization energy is so high that boron is always covalent. Second is oxidation state. Due to Ns2 and P1 configuration of the valence shell, group 13 elements are expected to be trivalent, but there is increase in ability to form univalent compounds on moving down the group. The oxidation state of boron and aluminium is +3, while gallium, indium and thallium show oxidation state of both +3 and +1. It is due to inert pair effect. Third one is metallic character or reducing power. The order is as shown. The increase in metallic character from boron to aluminium due to increase in atomic size. But gallium, indium and thallium do not follow the trend. They follow immediately after a row of 10 transition elements and thus have 10 d electrons, which are less efficient for shielding the nuclear charge than sp electrons. Thus outermost electrons, being more firmly held by the nucleus, are more difficult to remove than expected. This results to decrease in size as well as decrease in metallic character than would be expected. This phenomena is known as d block contraction. Similarly, for thallium, which is followed immediately after 14 F block elements, there is much change in the size and metallic character of it. It is due to the lanthanide contraction, which is due to the F block elements. Note that in general the size increase down the group but is less than as expected. Next property is acidic character. From boron to thallium, acidic character decrease and basic character increase because ionization energy increases. Thus we find that boron hydroxide and B2O3 boron oxide are acidic. Aluminium hydroxide and aluminium oxides are amphoteric. Gallium hydroxide and gallium oxides are amphoteric, and indium oxide, thallium hydroxide are basic. Boron
Nitrocalcite and borosite. So electronic configuration is Ns2 and P1 and has 3 valence electrons. Can exist as dimeric form as diborane. BS3 is an electron deficient molecule. It has 6 electrons and a vacant orbital, so it is used as an electrophile in organic reactions. Borax is used for cleaning and washing purpose. Aluminium was classified as precious metal during 19th century. Napoleon III gave aluminium cutlery to his most valuable guest. All other guests had to eat with gold cutlery. Physical state. Boron is a non-metal. Aluminium, indium, gallium are metalloids. Gallium has the second lowest melting point after mercury. It remains in liquid phase even at high temperatures. Amphoteric. Aluminium hydroxide is amphoteric. Strength between aluminium oxide and aluminium and oxygen and hydrogen is same. Aluminium is used in tins, aeroplanes and even in iPhones. Indium is used in display screens of television and mobiles. Thallium is used as rat poison. Next we'll talk about extraction of boron. It includes 2 steps. First is preparation of boric anhydride. So this is the reaction. The fused mass is extracted with calcium carbonate remains filtrate and insoluble containing sodium metaborate. By obtained borax crystals, borax is put to crystallization. The remaining solution is treated with carbon dioxide. The method 1 is followed. In method 3, suspension of solemanite mineral in water is formed and sulfur oxide gas is passed to obtain crystals of boric acid on cooling. So this is the reaction. Second is reduction, B2O3. In method 1, to oxidize unreacted metal M, the fused mass is stirred with iron rod. The mass is then boiled with dilute HCl to obtain insoluble amorphous boron powder which is 95% pure. Method 2 is modern method. A fused mixture containing magnesium fluoride, boric anhydride and magnesium oxide at 1100 degrees Celsius is electrolyzed in a carbon crucible anode. Iron rod is used as cathode. So these are the reactions occurred at cathode and anode. In third method, to obtain crystalline boron in small amounts, B2O3 is reduced with aluminium powder. Removal of aluminium is made by heating the fused mass with sodium hydroxide solution. Next is chemical properties of boron. Boron is unaffected by water under ordinary conditions. But the following reaction occurs when it reacts with water or steam. Amorphous boron burns in air at 700 degrees Celsius with a reddish flame, formed oxide and nitride. Boron is unaffected by reducing acids. With oxidizing acids, it gives boric acid. Boron dissolves is fused alkalis liberating hydrogen. Generally, boron forms non-stoichiometric compounds with metals. Action of non-metals. These are the reactions. Uses. Boron carbide rods are used to control nuclear reactions. Boron has a very high cross section for capturing the neutrons. Also, to make boron of having an even number of neutrons, boron absorbs neutrons. Diborans, B2H6. Structure and physical properties. In diborane, the bridge hydrogens form abnormal 3-centered 2-electron or banana-shaped bonds with 2 boron atoms. For having delocalized molecular orbital covering all 3 nuclei, an sp3 hybrid orbital from each boron atom overlaps with one s orbital of hydrogen. Diborane is highly reactive and colorless gas with disagreeable odor. It is used as a catalyst in polymerization reactions and as a reducing agent in organic reactions. So this is how it is prepared. Chemical properties. It is instantly hydrolyzed by aqueous alkali or water. It catches fire spontaneously in air and explodes with dioxygen. Thus in the laboratory, diborane is handled in a vacuum frame. Some other reactions of diborane are as follows. These are the reactions with ammonia and amines. Borazole is called inorganic benzene due to its similar structure and aromatic character. Boron nitride is a white slippery solid called inorganic graphite which has a layer structure similar to graphite. Next is orthoboric acid H3BO3 structure and physical properties. Orthoboric acid is a Lewis acid and better written as BOH whole thrice. It is a weak monobasic acid sparingly soluble in water. BOH whole thrice alone is not titrated with sodium hydroxide as a sharp end point is not obtained. However, if a cis diol is added, then boron hydroxide behaves as a strong monobasic acid and can be titrated with sodium hydroxide using phenolphthalein as indicator. Cis diols form stable complexes with BOH whole 4 negative, thus effectively removing them and carrying the reaction forward. So now chemical properties. First is effect of heat. Thus B2O3 is also called boric anhydride as it is an anhydride of boric acid. Second, water is removed by concentrated H2SO4 and the mixture burns with green flame. This is used as a test for boron compounds. Third is boric acid dissolves in HF aqueous to give fluoroboric acid HbF4, which is a strong acid. In dry HF, borates give BF3 which burns with a green color flame. Uses. Boric acid is used as an antiseptic and in glass industry and eye wash under the name boric lotion. Next is borax. Borax is better written as in this formula having 8 water molecules and the ion associated with sodium or Na positive. Chemical properties. When borax dissolves in water, equal amounts of weak acid and its salt are formed, thus, it is used as a buffer. Second, borax will react with 2 moles of acid because only these species are formed will react with H positive. Methyl oranges are used as the indicator. It is unaffected by the boric acid formed. Borax bead test. Metaborates of many transition elements have characteristic colors, and this provides a means of identifying the metal through this test. Uses. In analytical chemistry, it is used as borax bead test. Used as flame retardant for wood and fabric, used in glass industry, used as a flux in silver soldering and brazing. So the second element of group 13 is aluminium. Thermodynamically, aluminium should react with water and air, but in fact it is stable in both. As very thin oxide film of aluminium oxide is formed on the surface and protects it due to this resistance to high thermal conductivity and corrosion. It is used in making domestic utensils. Reduction of some metal oxides like manganese oxide and chromium oxide requires temperature high enough for carbon to be used as a reducing agent. Thus, aluminium, a highly electropositive metal, which on oxidation liberates a large amount of energy to aluminium oxide, which is used as a reducing agent. This is known as thermite process. The thermite reaction is as follows. Aluminium metal is moderately soft but lighter and much stronger when alloyed with metals. Some alloys of aluminium are these, and these are the uses: magnesium, duralium, aluminium bronze, and alnico. Magnesium is used in construction of airships and balances. Duralium is used in aeroplanes and automobile parts. Aluminium bronze is used to make utensils, cheap artificial jewelry, and alnico is used to make permanent magnet. Aluminium is amphoteric, hence dissolves in both acids and bases. However, concentrated nitric acid renders it passive due to the formation of a protective oxide layer. Aluminium oxide, alumina. Alumina is a white crystalline powder insoluble in water. It is quite unreactive, stable, and amphoteric in nature. The alpha form of aluminium oxide called corundum and found as mineral in nature. Aluminium trichloride AlCl3. Aluminium trichloride exists as a dimer, thus attaining an octet of electrons. It is largely covalent when reacts with a non-polar solvent such as benzene. However, when dissolved in water, the high enthalpy of hydration is sufficient to break the covalent dimer into this species and 3Cl negative ions. At low temperature, AlCl3 exists as a close packed lattice of Cl negative with aluminium 3 positive occupying octahedral holes. Crystalline AlCl3 exists as AlCl3 and 6 molecules of water. On heating, it cannot give anhydrous salt just like MgCl2 and 6 molecules of water. Instead, it undergoes hydrolysis on heating. The anhydrous compound is prepared by action of dry chlorine gas on aluminium or alumina. So now let's talk about group 14 elements. Metallic character. On moving down the group, metallic character decreases. Carbon and silicon are known metals. Germanium is a metalloid and tin and lead are metals. Oxidation state. Oxidation state of carbon and silicon is +4, while for germanium, tin and lead it has value of both +4 and +2 by inert pair effect. Next is catenation. Carbon has the property of linking to other carbon atoms, forming long chains due to its smaller size and high electronegativity. However, on moving down the group, the tendency for catenation decreases in the order. Carbon and its compounds. Allotropy. Carbon exists in a large number of allotropic forms. Two main forms are diamond and graphite. So these are the properties of diamond and graphite. Diamond is extremely unreactive, colorless, non-conductor and shows brilliant shine due to total internal reflection. The structure comprises of sp3 hybrid carbon atoms forming sigma bonds and arranged tetrahedrally. Graphite is quite reactive and soft. It has a structure with layers held together by weak van der Waals forces. Each sheet consists of hybridized carbon atoms that are covalently bonded to 3 carbon atoms by sigma bonds. The fourth electron is in unhybridized p orbital and forms a partial pi bond. So electronic configuration is ns2np2. Reactivity. The carbon family elements tend to be fairly unreactive. The elements tend to form covalent compounds, though tin and lead also form ionic compounds. Carbides. Carbon combines with other elements and forms carbides. These are considered as the hardest compounds. Chemical properties. Water gas is made by blow of air through white or red hot coke. Water coke is actually the mixture of hydrogen gas and carbon monoxide. All allotropes burn in oxygen to form carbon dioxide. Producer gas is made by blow of air through red hot coke. Producer gas is a mixture of carbon monoxide and nitrogen. Carbon as reducing agent. Carbon acts as a good reducing agent in most of the reactions. Carbon as oxygen acceptor. Preparation of carbon monoxide. In laboratory, it is prepared by dehydrating forming acid with concentrated H2SO4. These are the another methods of preparing carbon monoxide. Next is preparation of carbon dioxide. The most important industrial source is as a byproduct from the manufacture of hydrogen for making ammonia. It is recovered from alcoholic fermentation. It is obtained by heating hydrocarbons. In laboratory, carbon dioxide is prepared by the action of dilute acids on carbonates. Next is silicones. They are groups of organosilicon polymers containing SiO-Si linkages. Preparation. They are formed by the hydrolysis of alkyl or aryl substituted chlorosilanes formed by reaction Grignard reagent and silicon tetrachloride and their subsequent polymerization. So these are the reactions involved in the formation of silicones. Properties of silicones are R3SiCl is a chain stopping unit and reduces polymer size as it blocks the end of chain, while R3SiCl is used to produce new cross links and increase polymerization. Silicones are electrical insulators, water repellent, strong and inert. Their boiling point and viscosity increases with increase in chain length. Silicones are stable towards heat. It is the order of stability which varies with attaching alkyls in the order. Being water repellent, silicones are used for treating glassware and fabrics. They are also used as silicone rubbers and hydraulic fluids. Next is silicates. Silicates are derivatives of silicic and SiOH4 or H2SiO4. They have basic tetrahedral units SiO4 4 negative and silicon oxygen bond is considered to be 50% ionic and 50% covalent. Preparation. Silicates can be prepared in an electrical furnace at about 1400 degrees Celsius by fusing an alkali metal carbonate with sand. Classification of silicate minerals. First is orthosilicates. These contain single discrete unit of SiO4 4 negative tetrahedral. For example, zircon, gemstone, forestrite or olivine, phenacite and willemite. Number of shared oxygen atoms is 0. Next is pyrosilicates. These silicates contain 2 units of SiO4 4 negative joined along a corner containing oxygen atoms. These are also called as island silicates. So this is the structure of pyrosilicates. Examples are thortevitite and hemimorphite. Number of shared oxygen atoms are 1. Cyclic structure. They are also known as ring silicates having general formula SiO3 and 2N negative. Structure and examples of cyclic silicates containing Si3O96 negative ions are given below. Examples are beryl and wollastonite. Number of shared oxygen atoms are 2 in this type of silicates. Next is chain silicates. These are formed by sharing two O2 atoms of each tetrahedral units. Anions of chain silicates have two general formula. Spodumene diphosphide and tremolite are examples of these type of silicates. This is the structure of chain silicates. Next is two-dimensional sheet silicates. In such silicates, 3 oxygen atoms of each tetrahedral are shared with adjacent SiO4 negative tetrahedral. Such sharing forms two-dimensional sheet structure with journal Si2O6N whole 2N negative. Examples are tail and kaolin. Number of shared oxygen atoms are 3 in this case. Next is 3D silicates. These silicates involve all 4 oxygen atoms in sharing with adjacent SiO4 negative tetrahedral. For example, quartz, zeolites, ultramarines and feldspars. Here all 4 oxygen atoms are shared. Next concept is tin and its compounds. Tin is a soft, white, lustrous, malleable metal. It produces a cracking sound called tin cry whenever it is bent. Properties. Tin reacts with steam to give tin oxide and hydrogen gas. It dissolves in dilute nitric acid forming tin SnNO3 whole twice. It is rapidly attracted by hot alkalis and slowly by cold alkalis, thus it is amphoteric. Tin is used in tin plating, coating iron or steel sheets with tin and making alloys like solder and bronze. Sn2 positive and Sn4 positive. Tin ion exists in two states, with the +6 state being more stable. SnO2 is called as cassiterite and found as a mineral in nature. The other oxides, SnO, is obtained by heating stannous oxalate and is less stable in nature. Germanium is a rare element used in the manufacturing of semiconductor devices. The physical and chemical properties of germanium are very similar to those of silicon. Germanium is grey-white in color and forms crystal structure. Silicon is the second most common element in the Earth's crust after oxygen, and it is a backbone of mineral world. Silicon is used extensively as a semiconductor in solid-state devices in the computer and microelectronic industries. Tin is malleable, ductile and crystalline. It is a superconductor at low temperatures. Tin reacts with bases, acids, salts and strong acids. Tin chlorides are good reducing agents and often used to reduce iron ores. Tin fluoride is often the anti-cavity fluoride additives in toothpaste. Lead is a soft malleable metal with a low melting point. Lead is toxic to humans, especially children. Even low levels of exposure can cause nervous system damage and can prevent proper production of hemoglobin. Its oxides have many industrial uses as oxidizing agents such as cathodes in lead acid storage cells. So points to remember are: carbon has the highest melting sublimation point of the elements. The melting point of diamond is 3550 degrees Celsius, with the sublimation point of carbon is around 3800 degrees Celsius. Both SnO and SnO2 are amphoteric, but SnO is slightly more basic than SnO2 and a good reducing agent too. Among halides, stannous chloride and stannic chloride are more important. SnCl2 exists as a dihydrate which undergoes hydrolysis on heating. The anhydrous salt SnCl2 is obtained by reaction of Sn with a calculated quantity of HgCl2. Excess of HgCl2 results in the formation of stannic chloride. Most of the reactions of SnCl2 are due to its reducing character. It reduces MnO4 negative to Mn2 positive, Cr2O72 negative to Cr3 positive, and itself gets oxidized to Sn4 positive. Lead and its compounds. Lead is a bluish grey soft metal which is extremely poisonous and can be cut with a knife. Lead often appears more unreactive than expected from its standard electrode potential. The unreactiveness of lead is due to the surface coating of basic carbonate, which forms over lead when exposure to air and moisture. Thus, lead is unaffected by water. Lead is amphoteric, hence dissolved in both acids and hot alkalis similar to tin. In alkali forms, plumbates like these. However, due to formation of surface coating of PbCl2, lead does not dissolve in concentrated HCl. Lead is used in making lead chamber for S2SO4 plant and certain alloys like solder oxides. Lead exists as Pb2 positive and Pb4 positive, with Pb2 positive being more stable because of inert pair effect, which increases the stability of plus 2 state while going down the group. Oxide formation is shown as PbO and PbO2 are both amphoteric and dissolved in both acids and bases. Pb3O4 or red lead may be represented as 2PbO dot PbO2 and is used in paint to prevent the rusting of iron and steel. Lead oxide litharge is commercially important and is used in large amounts to make lead glass. PbO2 is used as a strong oxidizing agent and produced in lead storage batteries. Chlorides. They are prepared by passing lead through a current of chlorine gas. The reaction is shown. Dissolving Pb2 positive salt in HCl produces PbCl2 PbCl4. PbCl4 is